Okay, so there's a class of algorithm that is all about clustering data. Maybe you have stars in the sky, and you're taking automated pictures with some sort of deep field telescope, and you want to group the stars into, or the galaxies maybe into clusters, or maybe you are scanning a colloidal suspension, and you get pictures, and with your human eye you can see that the things are clustered up into groups, but you have a great amount of data, and so you want a computer to look at that data, analyze it for you, and group these things into clusters. Just real quick, let's look at an example. So here are two sort of model clusters. And what we're going to be doing today is a particular algorithm for cluster sorting. Let me make sure the sound coming through. Yes, okay, good. A particular algorithm for cluster sorting, and the name of the algorithm is Fast Search and Find of Density Peaks, and Rodriguez and Allessandro. Anyway, Rodriguez and Allessandro are the two people who developed it. Came out in 2014, and real quick, Fast Search and Find. Let's see if it comes up. Of density peaks. If you want to read the scientific paper that it's based on, you can at least read the abstract here, and I'll put a link to this in the description. So, how does this algorithm work? I think this is the first algorithm of this scale that I ever attempted to understand, and it's actually pretty intuitive. So even if you don't have a background in this kind of stuff, the core intuition is something that I think anybody can get. So here are our two model clusters. Now, as human beings, we can look at them and go, oh, there's a cluster, and there's a cluster. But how do we do that? And how can we take our intuitions and convert it into something that a computer can do? Well, let's have a shot. The dots have a property that is so obvious you might not even bother to notice it, which is some dots are closer to more dots than other dots are. This dot's pretty close to a fair number of dots, and this dot is kind of far away from more dots. We could have an extreme case where we have some dot over here, and this dot really isn't close to any dots. Again, almost too mundane to bother pointing out. We can go a step further and say there's probably, in each one of these clusters, there's probably some dot that is closer to more dots than any of the dots around it. So this dot, this dot is close to pretty much every single dot around it, and in this cluster it would be this dot. And so we could sort of broaden that out and say there's probably some ranking in each of these clusters of how many dots these dots are close to. And we could if we could find some way to describe that amount of closeness numerically, what we can do then is we can ask the question for each one of these dots, where is the dot that is closest to it that has a higher density? And so let's ask that question. For this dot, it's probably that dot. That is the closest dot with a higher density, a higher degree of closeness, but that's where density comes in the fast search and find of density peaks. So we could draw a little arrow and say, well, that's the closest dot for this dot that has higher density. And then we could do the same thing for this dot. That's the closest dot that has a higher density. And likewise, for these two, this center dot is the closest dot with a higher density. And when we ask that question for this dot, we have to look further than this cluster, because there's no dot we can see in this cluster that is closer to more dots than this dot. And in fact, I don't think on this particular set of clusters that I've drawn, there isn't another dot that is closer to more dots. There is not another dot that has a higher density. And so we'll come back to this dot. But there's no dot that has more greater density than this dot among these dots. So let's ask the same question for these dots now. Well, that dot is the closest one with higher density for this one, and likewise, all of these are going to be pointing into the same dot. Now, when we asked that question about this dot, where is the nearest dot to it that has a higher density, we have to leave this cluster. And if we had more clusters, let's assume that this dot remained the densest, having the greatest density of all the dots that, of all the clusters that we would add. All the other cluster centers would have to look outside of their cluster to find a dot that had higher density. Maybe they'd go to this dot, maybe they'd go down here, but they'd have to find another. They'd have to find a dot outside of their immediate cluster. And this property of being far away from dots with higher density is, while simultaneously having a high density, those two qualities together distinguish the centers of clusters. This dot here is far away from dots of higher density, long way, but it itself does not have a high density. And I don't know, let's say this dot here. This dot has high density, but it's very close to dots of higher density. So when we consider these two properties, being far away from dots of higher density and or data points, that's maybe a more technical term, being far away from points of higher density and having high density, those two qualities distinguish the center of clusters. Once we have distinguished cluster centers in this way, we can assign all the points that end up pointing to some center data point to a single data cluster. So all the data points that either point directly to this data point, or which by a chain of assignment ultimately are grouped with this point, all of those would become a single cluster. And likewise. And this guy, we'd have to make a decision. Do we somehow group him in here, or do we make him his own thing? Do we not consider him a cluster at all? And that's the idea. Get a measure of density for every single dot, and then compare how far you are away from dots of higher density. All right, so let's start coding. Everything. This is the link here to the article. I'll keep W3 schools there because I'll probably need it sometime during all this. Where all of our number processing is going to be done in NumPy, and it's really only NumPy and something to plot with that we need. Import make subplots. And then just a cosmetic thing. Let's see. Import plotly.io as pio, and this just makes the graphs are dark to fit with this dark theme, and then pio.templates.default is equal to plotly dark. There we go. All right, and in NP. Wow, that's a new one. Any other? Looks like no other syntax errors. Okay, so before we cluster the data, we need some data to cluster. Sorry, just making sure everything's recording. Okay, so let's make some data. We'll have NC be our number of clusters, and let's have a little fun with this. we'll have, let's make a random number of clusters. NP random dot rand, so that we will really have some randint, and it should be something between, I don't know, 4 on the low end, 10 on the high end, and so yeah, 4. Wouldn't want any more than 4, and if we do more than, well, let's stay in the single digits, somewhere between 4 and 9. So we'll just have some random number of clusters. But that being said, let's fix a random seed so that if we go back, you know, we can recreate np random. Is that a random seed? Is it in here? Let's see. If I don't remember how to do random seed. Random seed in Python. This is a legacy. Okay. np.random. Oh yeah, we wanted so random.seed. np.random.seed. And let's just make sure. Okay, yeah. So if you read this thing, there's apparently a better way to do it now. I don't know that, and I'm not going to explore it right now. Let's have it be, I don't know, 1,000? Does that seem like a reasonable random seed? Let's run that. Okay, good. And let's see what our NC is. Well, it'll vary every time. It'll keep varying into, well, no, it won't, because we've got a random seed set. So let's get a random number of particles per so we're going to have 7 clusters. Let's get a random number of, so PPC will be particles per cluster. PPC will np.random.randint, and let's have between 10 and 20, say 20 particles per cluster. And let's have our size equal to whatever our NC is. So there we go. Let's take a look at PPC and see what we're going to be working with. Okay, so all right, fair enough. That's what I told it to do, so it makes sense that that's what it did. There's a puppy who keeps pushing open the kitchen door, and I get noise from the TV next door. Okay. All right. So we've got some random number of clusters. We've got some random number of particles per cluster. Now let's get coordinates. Let's make coordinates for them all. So P is going to be, that's the list where we'll end up keeping everything. And let's just go through the random. Well, let's just go through these seeds one by one, and we'll generate what we need. So for I in range NC, so for once for each number of clusters, we'll make some temporary list B is equal to np dot random normal. I say normal, boy, that it is kind of loud. Okay, so these points will be normally distributed about. We need first we need centers for our seeds, and then we'll locate these around them. So what we need, let's see, before we do all our points, we need centers to locate them around. So cent, let's see, clusters, centers, np at random not normal, and yeah, so we've got 7 clusters, right? So we want, for each cluster, we want a center, and let's actually have these be randint as well, so that they'll be spread out a little bit more. NP random randint, and then we let's have our clusters in a space between. If we're gonna have to up to 7, let's have it in a 20 by 20 unit cube. So we'll say all these coordinates have to exist within that 20 by 20 unit cube. We won't go into any negative space. So between 0 and 20, and the size. So the size is, we want as many rows as we have clusters. So the size will be NC, and we want 3 columns. We'll be in 3-dimensional space, so we want 3 spots for each, 3 coordinates for each cluster. And I think that's good. Let's take a look. Let's see where we'll be centered. Okay, so here's where our centers are. Okay, all right, yeah. Now that we've got our cluster centers, let's get our data points. So P, I typed before, that's where we're going to store all of our data points as we generate them. So for I in range NC, so once for each cluster, we'll say B is equal to np.random.normal. So here's where we'll have things be normally distributed. np.random.normal. The location is where these things will be centered, and so they'll be centered around the cluster centers. So each time we do this, we clust cent, and specifically we want the ith row, and we want all columns. That'll be the center that we create these things around. And then, so the next thing we want is when they say scale, that's the same thing as standard deviation. And so, I don't know. We can play with that. For now, I'm gonna say 3. And then the size. The size of, so for each one of these, we'll be generating, for between 10 and 20 rows, each row corresponding to one set of coordinates, and then each set of coordinates has 3 coordinates. So we want PPC, we want the ith entry in PPC. That's how many rows we're going to have. Rows corresponding to the number of particles around in that cluster. And we want 3 coordinates. What is that? And then p.append b. Is that going to work? Let's find out. Appears to have. All right. So let's go p. Let's take a look at p. Okay. All right. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. There we go. Those look like some clusters. All right. The only thing, notice right now we've got I set P to be a list. That's, those brackets mean it's a list. And right now it's a list of lists. So let's combine these all into one nice long column. So we'll say P is equal to np.concatenate P. And I think that should do it. So let's take a look now. P. And just like that, we've got, look at all these beautiful coordinates here. Let's take a look at how many. Oh. It's a tuple. Really? It's a tuple? Huh. Can I make it into an array? Do I need to? tuple into array. A little Googling never hurt anybody. Turn tuple into array. I should have said Python. List. How do I connect? I don't want to combine these things into one list. I just want to make them into convert list of lists into matrix. Yeah, this is what I want to do. Will that work? np.array. I feel like I've tried this before and it hasn't worked. I don't know why. Let's take a look at P now. P.shape. Can we get a shape? No, because it's still a tuple. I'm not gonna spend all my time on this, but oh well. I think we might be able to keep going. Just wish it was not a tuple. Okay, so if you remember, we want to get some measure of density for each particle, and to do that, we need to know how far every particle is away from every other particle, and then we'll weight close particles by exponential decay. We'll raise everything to a negative power, and so really big numbers will become really small, and really small numbers will become really big, and in that way, particles that have lots of short distances from other particles will get a really big density value. That's the name of the game. So let's start to get a matrix of distances. I'm still not at this point totally comfortable doing broadcasting, which is a way of doing certain things that you might normally do in loops instead with vectors. It's very concise, it's very convenient, but it's definitely a learned skill. So I'm going to go P. I recall I want my nuns on the outside. This is going to allow me to subtract every for the first row, subtract, I think, either it from every other row or every other row from it, and then for the second row, do the same thing, subtract it from every other row or every other row from it. We'll actually check that in a moment, because I don't remember which one it is. So it's a way to sort of do matrixy things really fast. P, all, and none. So let's take a look at this. And dist. So let's take a look at dist, but let's also take a look at the first, I don't know, two or three rows of P. So P. 0, 3, and then all columns, and there we go, and then dist. And this way we'll be able to, I'll be able to remember more confidently what's actually happening here. Okay, so there we go. There are our first three coordinates, and so we can just get a quick sense here of what's being subtracted from what. So first, row 1 is subtracted from itself, resulting in these zeros, and then it looks like row 1 is subtracted from row 2. Okay, so that's what's going on. Row 1 subtracted from row 1, row 1 subtracted from row 2. So this first group will be row 1 subtracted from all of the rows, and then the second group will be row 2 subtracted from all the rows, and that's the idea. Okay, so we've done that. Now all this is just to find the distance between one point and another. So to find the distance between 2 points, you subtract all the coordinates one from another. You square all of them, you add them up, and take the square root. It's pretty much the same as the Pythagorean theorem. A squared plus b squared is equal to c squared. Only in this case we have a squared plus b squared plus c squared is equal to d squared. All right. So we've got that. Let's square all our values to get rid of any negative signs that may be lurking. Negative sign's gone. All right, now let's sum all these critters up. And NP sum. I'm going to specify an axis. Axis equal to -1, whatever the outermost axis is. Let's and then I guess we'll take the square root, but let's take a look at that just to make sure that things are as they ought be. Okay, that looks like more or less like it should. 0.5. All right, and so here we take the square root, and let's take. We don't need this anymore. That was just momentary. Okay. So this is the distance of all points from each other. Cool. So now that we've got that, okay. So it is an ND array. That's good. Can we somehow magically now use shape? Or are we still in trouble because shape is a tuple? Nope. Okay. I don't know why I keep trying. All right. So we've got our distance matrix. Now let's find some distance to normalize all of our distances by. Okay, so let's see, d-norm, our normalizing distance, will be, say, the 5th percentile of all distances. Actually, you know what? We're doing a lot of stuff here. We should take a look at what our data looks like before we get really invested. So fig is equal to make subplots, and then we fig dot add scatter 3D, and then we'll say x is equal to p all rows, the 0th column, and y is equal to p all rows and the 1st column, and z is equal to all rows of p and the 2nd column, because Python indexes from 0. Trying to do this problem at an earlier time, all my points were graphing on like this angled plane, and I couldn't understand why that was happening. And I eventually realized that I was graphing my z as I think column 1 or column 0 rather than column 2. So it was of course there was a constant relationship between my coordinates at some points. It's amazing how you can spend, a long time staring at the screen and not see something like that. So mode is equal to markers. There we go. And let's also make the default size for the figures to be is pretty large. So we're going to update the layout. Fig update layout, and we'll have the width be 800 and the height be 600. There we go. Okay. So first impression, that standard deviation is a little large, so let's make it smaller. 2, say? Oh. We'll get back to you, dnorm, don't worry. Let's tighten these clusters up a little bit. That's still pretty, I wonder if we want to get these things, let's try a little tighter, but we might need to spread them out a little bit more, spread the actual cluster centers out a little bit more. And so, okay, yeah, so we've definitely got some, oh, well, 1, 2, 3, 4, 5, 6, 7. Yeah, but these two are awfully close. And that's certainly a realistic thing that could happen. But for this example, I want it to be very, very clear. Let's see if this can be easy and just try a different random seed. And, okay. Those look like 5 clusters. Let's see if our NC is actually 5. Okay, great. So we've got some number, and that's the wonderful thing about randomly generating everything, is that you can get a totally different scenario very quickly. So, all right. So now that we've seen, can we afford to make our? Nah, that's good. That's good. Now that we've taken a look at our data, let's go ahead and continue with our distance matrices. So let's say let's think about what a good cutoff distance would be for what we're looking at here. Well, actually, as a rule, unless I can think of a really compelling reason right now, I'll probably say that weights in the under the 5th percentile of distances under the 5th percentile will be weighted favorably, and those over will be weighted unfavorably. We can try that and see how it works. So dnorm is equal to NP percentile. NP percentile, and let's see, so the percentile of the distances in dist, and then yeah, we can do the 5th percentile. 5th percentile. Let's do that and see what dnorm is. Dnorm. Keeping in mind that our scale here is from about 1 to 20. So, if I had to say, the things in here are within, that's 5, 10, 13, 10. That's about a span of 5, I think. No, why is 0 there? Oh, no, that's 0, right? So 0 to 5. So in about a span of 5, so if you're within 5, it's of something, it's a good chance that it's in your same cluster. Not necessarily, but there's a favorable chance. All right, so let's take a look at dnorm. Well, that's certainly smaller than 5, but that way we won't have these these guys feeding into each other. Okay, so yeah, let's do that. Let's have that be our dnorm. So let's get another. We'll call it rho. So this will be our density that we've been talking about this whole time. And we'll say np.exp. And we will just put our whole distance matrix into the top, and we'll divide each value by dnorm, and we will put a negative exponent. So anything that is larger than dnorm will become smaller. And there we go. Am I missing something? Looks kosher. Let's take a look at rho. Okay. All right. And there's our density that we've been talking about. Now let's get a total density. So we'll go. Oh, in fact, we could do that now. We don't need to do that in a separate step. And so we'll go np sum. Felt like there was something else that was supposed to happen on this line. np sum of all this. And what axis do we want to sum along? Well, unless I miss my guess, these should be symmetric matrices, so it shouldn't matter whether we sum over rows or columns. We can actually check that, but axis is equal to 1. And then we'll take a look at it. All right. Okay. Pretty close to one another. A few high values in the 6s. Not a ton. Okay. All right. We'll see. Just out of curiosity, does that stay 4.88 and 607 if we add along the 0th axis? Yeah, okay, so it doesn't matter in this particular problem which axis we add up along, because it's a symmetric, the matrix is symmetric diagonally. All right, now let's think out our next step. Our next step, we want to compare the density. Our ultimate goal is that for each one of these points, we want to find the point nearest it that has a higher density. And so the first thing we'll do is we'll filter out all the points that have a lower density. And we'll do that with a Boolean matrix, rho ij. And we'll need to do a little bit more broadcasting here. And it's not my strongest suit, but hopefully by using it more, it'll get stronger. None. So here we're going to be having a vector interact with itself to create a matrix. So rho none greater than rho none. I shouldn't just say rho none. Rho none and all greater than rho all and none. It sounds kind of cosmic when you say it that way, or philosophical or something. All and none is greater than none at all. And then let's take a look at rho ij. Rho ij. Okay. All right. Good deal. Let's just to make sure that we've got what we want. Let's take a look at rho and make sure that the answers that we've got make sense. So we're at, and that'll also again help us build a little bit more of a grounding into what's going on with this broadcasting. So we're doing it this way. We're getting false, true, and false. So we're asking, is something bigger than this, or is this bigger than something? So this is not bigger than itself. So we'll always have a false in the diagonal, because we'll be asking, is 0.1 denser than itself and 0.2 denser than itself? So I think what we're asking, based on this true in the second, this second entry is bigger than the first entry. So what we're asking here is, for the ith entry, if we start with the ith entry, we're repeatedly asking, is the jth entry bigger than the ith entry? And that makes this whole row. So is entry 2 bigger than entry, or entry 1 bigger than entry 0? Yes, it is. So we get a true. And then is this entry 2 bigger than entry 0? No, it's not, and so forth. And we've got large values at the end. They are all bigger than this, so we get true, true, true. Okay. So rho ij looking good. Now, as I said before, this is to filter out the things that don't have higher density, so we can find the closest thing that does have a higher density. And let's see, distances. So if we convert all of the entries in here that are false to true, and true and false are synonymous with 1 and 0 in most of the computing languages that I've run into, which is not a ton, but so if we convert false to true and true to false in this particular matrix, and then everywhere that relative to some other point, a point has less density, we'll have a 1. We can multiply all those points by the maximum density, and then we can add this new matrix to our old distance matrix, and now there will be some whatever the minimum distance point is in each row. It will still be a point that has greater density than the whatever particle corresponds to the row that we're looking at. I hope that made some sense. If not, bear with me. So let's see. I'll say min, and we'll say nearest. No, don't need a capital. Nearest dense. Nearest dense is going to be, and we'll go NP logical not row ij. So that'll switch all falses to trues and trues to false, and we'll multiply that by NP max, whatever the maximum value in distance is in the distance matrix, and then we'll add it to dist. There we go. All right. So this will give us a new matrix, and in each row there will be almost each row there will be some entry that is the minimum distance to a point of higher density, because we've made all the points of lower density have larger distance, so we won't even be looking at them. Artificially, we've made them have larger distance. Okay, so we want to find the minimum in here. np.min, and np.min. Yeah. Once again, I think we need to do it along a particular axis. Because if we just say np min, it'll find the minimum in the whole thing. Yeah, we want to do it along the horizontal axis, I believe. Yeah, we want to be moving in that direction. So let's do it, and then let's take a look. Nearest dense. I know I spent a lot of time checking the things that I've just done, but it's amazing how much time. So this is the distance to the nearest particle of higher density for each particle, with one exception. There is some particle that is going to have a greater density than all the other particles, and if you go and read Rodriguez and Allessandro's paper, they talk about setting it that way artificially, and we've actually already done that. But because when we do this inequality, we're asking for each point, what points have greater density than it, and there is no point that has greater density than the point of greatest density. So when we in this initial matrix, that's just a row of all zeros for that particular value, and for the highest density particle. And then when we do this thing, we've artificially set every single entry in that row to be the maximum distance. So we've already taken care of it, kind of without meaning to. At least the first time, I was like, wait, I didn't do that. Why did it still work? That's why. And so now let's see. So now we've got. We also want the index. We want the location in our array of this nearest. So we'll call this nearest IDX, and we'll np.argmin, very useful function argmin, and we'll just copy the same expression. Argmin finds the argument or the index of the minimum, and that's exactly what we want. We've got the value of the minimum. Now we want the location of the minimum. And let's take a look at these things. NP column stack, and we'll go nearest IDX and nearest dense. There's something to be said for shorter names, but for something like this where there's a lot of unfamiliar ideas floating around, or also I may come back to this in 3 months and not remember any of this, then descriptive names are really helpful for me. Let's take a look. Okay, so here for every point, the index of the point nearest to it with a higher density and the distance to that point. And that must 20. I bet that's our point of highest distance. Point of highest density, because that's a very large value. 16, 23. Shouldn't it be 2? Yeah. Anyway, yeah, that's most likely our point of highest density. We'll see if 24 comes up again. Okay, so there we go. What to do next? Let's recap. We've got a list of the indices of the point with highest density near to us, and we've got a list of distances to those points. So if we revisit our original scheme, we remember that the cluster centers had these two qualities, that they were further away from, far away from points of higher density, and they were themselves very dense. So we could take a quick look if we want and see graph the density against the nearest distance, and that'll probably stick out. Not an essential thing to do, but kind of neat and maybe helpful conceptually. So let's pop that again. Let's see. Let's do this down here. Fig 2 is equal to make subplots, and fig 2 dot add scatter, but we don't want to add scatter 3D. And let's make x our density, and we'll make y our distance to other particles. And our cluster centers should stand out very visibly on this chart. So just to recall what we called them, our density was a vector called rho, and our distance was nearest dense. So rho, nearest dense, let's do it. X is equal to rho, y is equal to nearest dense, and mode is equal to markers. Let's update the figure. Making sure to change the name of the figure. It's always the danger when copy pasting, not changing things to meet the actual situation you're working with. All right. Okay, and just like I was hoping, there's 5 points that stand out really clearly, and there's that 23. That's the point of highest density, Yep, 6.9, 6.9. Yep, that's the point of highest density. Okay, cool. So, what next? Our next thing is we want to start, well, if we're given a random data set that we've never seen before, and maybe it's in too high a dimension to visualize, we can't just say, oh, well, we know we've got how many clusters. Let's gather everything up into the clusters. That kind of defeats the purpose of what we're doing here is supposed to detect some number of clusters. And to do that, let's see. To do that, let's do a little bit more graphing. Boy, yeah, we're doing a lot of graphing. Fig 3. You know what? Let's get the sorted index, an index that's sorted by distance. So we want an index that gives a list that gives us this index, and then this index, and then this index, and so forth. Oh, no, this, and that will make this next step a little bit clearer. Okay, so let's see. What do we call it? We'll call it dist IDX. Dist IDX is equal to np.argsort. Argsort. And argsort gives a list of indices if they were to be sorted by their values, with their values sorted by the values that the indices refer to, from least to first. So if we were to sort, if what we're going to do is we're going to sort the arguments of all of our particles with respect to the particle's distance from other particles. All right, and np argsort. Already forgotten. Was it dist IDX? No, it was nearest dense. That's what it was. Nearest dense. Nearest dense. Argsort. Nearest dense. And argsort defaults to having. Let's actually take a look at it. Dist IDX. Argsort defaults to having the smallest of whatever the entry is, having its argument first, and the largest last. And I want the reverse for this particular case. So I'll go -1, ::, -1. That'll flip everything around. There, 24 is at the start. All right. Now a little bit of theory. So notice I have this very handsome graph drawn out. In a minute, I'll do this graph too, just so you can see it. But it's going to look like this here is distance. We've just sorted all of our particles by distance, for two particles of higher density, with the highest first and the lowest last. When we graph these points like this, we notice that there are very few points which have a relatively high distance to other points of high density. Those are our cluster centers. And we have a large number of points that are low distance from points from higher density. And there tends to be this big gap. There will be this sort of long, flat line, and then whoop. I think I did. Didn't I already do this graph earlier? No, I guess not. So, when looking at this graph, some smart person made the observation that if you were to draw a line connecting the point of highest distance and the point of lowest distance, if you were to draw that line, this point here would have the property of being either the furthest or one of the furthest points away. I say one of the furthest because I have done this a few times to make sure that everything works. And sometimes with my randomly generated data, I'll get a little kink up here, and it'll be this point here or this point here that are actually the furthest away. So it is worth checking out. point's just there for illustration, though. Well, anyway, so if we say that this point is the furthest away from the line, if we were to draw a straight line from each point to this line. And so what we're going to do is we're going to, in a mathematical way, we're going to find what these distances are for every point, and then the greatest distance should be this point here, ideally, and then we can just take the index of this point, and that index will, since Python indexes from 0, if this is the 5th point, its index will be 4, and it'll happen that there are four cluster centers. In our case, there'd be another point somewhere, there maybe. And there are 5 cluster centers. This will have, it's the 6th point, it will have an index of 5. So we can just take that and know that there are 5 cluster centers, and then we can start to group everything up and assign points to clusters once we know the number of clusters we have. So how do we get this distance? Well, it's going to kind of take you back to your high school or your college, basic vector math. That's what we're going to do. So if we subtract from this point's coordinates, the coordinates of this point, we'll get a vector that's pointing from this point to this point. It'll stretch that distance. It'll have some x value and some y value, and then we remember, because our ultimate goal is we want this distance from here to here. What we can do is also subtract this point's coordinate from every other point, and now notice that the line that we're looking for right here, if we were to draw a line that was orthogonal to this line, we'd end up with a right triangle. We'd end up with, for this, I'll draw it for this one. We've got a 90-degree angle here. This line is our hypotenuse. This line is the projection of our hypotenuse on our initial vector, and so if we calculate that projection, which we will do, first after getting this vector, we'll find the unit vector that points in this direction. Then we'll get all of these sort of hypotenuse lines, and then we will take the dot product between these lines and this line. That will, if we did it for this line, or for this line, say, that dot product will give us a scalar value, which is just a single number. It's not a list of numbers, not a vector, which I'll call d. And since this is not a vector, it needs to be multiplied by something to make it a vector. We want, this is a distance, but it's not a vector. It's just a value. So we'll multiply d by this little vector to get a unit vector in this direction, and then we will subtract this vector, which is the product of d and the unit vector. We will subtract that from this vector, and what's left will be this vector. And then we can get the norm of that vector, and voila, the norm is the distance, and we can find the point that has the greatest distance, which should be hopefully that point. And once we've identified that point with the greatest distance, we have the number of clusters. Okay, let's go to boom, boom, ba-boom. I'm accustomed now to doing this as a function, and so I'm going to keep doing it as a function, but it really wouldn't have to be in principle unless we were going to use it multiple times within this code. I will call it inflection. Def inflection. So what this is going to need to take in is this sorted matrix. This matrix sorted by this vector of distances sorted by which distances are the closest. So we'll just call it x for now. And let's be ready to call it down here, because there's some places you can go wrong with this. So inflection, we want to inflection. When we want to put into inflection. I went too far. No, I didn't. We want to put it into inflection nearest dense, but nearest dense sorted by this distance index. In fact, let's go ahead and graph that here. Dist IDX. Is that what we called it? Dist IDX, yeah. And then we'll just have this be regular old NP. Oh, you know what? Something that is going to become increasingly useful as we go on is the length of one of these things, just to know how many points we have. So we'll say that n, capital N, is the length of row. And let's do that, and then let's take a look at n just to make sure it makes sense. 77. Hey, that seems like a cool number. All right, so we've got 77 points. So here, will be NP A range n. That's just straight up the just to have some numbers. Uh-oh. NP ND array not callable. Ah. I swear I do this so frequently. I should avoid it by now. Okay. So here, this is there we go. We've got our 5 points. They're very clearly distinguishable. So looks like that will be our kink right there. It's just possible. Yeah, no, it's going to be the point that it's supposed to be, which is good, because who needs the headache of okay, so we've got our inflection. Our inflection is going to take in this argument. We're basically feeding this graph into our inflection function. All right, and then we'll go through the steps that we did. So we'll say that data is equal to, because we want to make this graph, we'll say data is equal to NP So we need 2 points in order to make it a graph. NP NP dot a range n. That's probably another vector, honestly, that I should be using. I should be calculating once. And x data. Okay. All right. So now we have effectively all of these data points, and it shouldn't really matter too much what these values actually mean. We just need this shape and this concept that these points here are high density, these points here are low density. All right. Now let's get that line, that first line that connects the first point and the last point. So that line is going to just look like this. It's going to be data, whatever the last point is, -1. Data is -1 meaning the last entry in that list of numbers, and data 0 being our first and largest point. And let's return data. All right, and oh, I did it again, didn't I? Or did I? Where? Nothing function method object is not subscriptable. B is equal to P dot arrange N. Will it return B? Return B. What does it think N is? What in the world? What's going on? Works fine here. P arrange N. Is it different in some way? Okay, it makes us a list of numbers from 0 to 76. That's what I wanted to do. It's really an issue here, huh? Built-in function. It's not like I'm not using parentheses. Oh, I made the opposite mistake. I need to not be using parentheses. Okay. Oh, yeah. All right, every moment a learning opportunity. And so let's get back our line values. Ooh. Okay. And we do need to put B in here. All right, and up. There we go. Huh. Thought it was 24. Well, we did change things up. That's right. That was before we moved our things further apart. Okay. So we've got that first line. Let's get the unit vector of that line, which will be, we'll call that UV for unit vector. UV, yeah, UV. And you know what? I was calling it line unit vector, so it's a friendly little variable name. So we've got our line unit vector, and so-called because it's the unit vector of the thing we've named line, and that's just going to be line divided by np dot linalg dot norm of the line. And let's return that. Let's return them both actually, just to make sure they make sense. And, okay, make sure we've got that, and then we've got this, and yeah, that looks like if we were to square these values and add them together, you know, that'd get smaller. That'd go to that'd become something smaller, as would the 2. And yeah, cool. All right, and let's just make sure the proportions are right. They are. Ish. Okay. Yeah. All right. So we've got that. We're now to the point where we've got this, and we've got this little unit vector. Now we need these hypotenuses, whatever the plural hypotenuse is. So say hype. Getting on the hype train, we will from each point, we will subtract that first data point. So we'll just say data data minus data 0. And we'll return that to height. All right. Boy, those are awfully similar. Well, but they're all about the same height, so it makes sense that the y component would be much smaller. All right, and yeah, that should be a whole number as well. Okay, cool. So now we've got that, and remember we wanted the next step is to get the for each one of these, we're going to get the dot product between them and the line. So we'll call that D for dot product, or distance, or other good words that start with D. D is equal to np dot np dot, and we'll have this be the dot product between between hype and the LUV, that unit vector. No. Sorry, we want it to be between that and line, because line is the full length vector, and we just want the projection on the unit vector, because all the dot products will be the same. They'll be one unit long. Okay, so let's return D, and we can do. Okay. Pretty large. Does that make sense? Does it make sense that is so large? Okay. That's gonna be, yeah, as we get further this way, we will have 80 times 80. That'll get pretty large, or something approaching 80 times 80. All right, so it doesn't seem crazy that we'd have something that's approaching 80 times 80. There, okay, good, makes sense. So that's the projection. Now let's multiply these values by the unit vector. There's not something else you need to do with the dot product, is there? Do you need to divide by something to make it be the projection, or is it the projection by itself? I should know that. For whatever reason, it's not in my head at the moment. So we multiply all these values by, so we've got an array of values, and we're going to multiply LUV, the unit vector, by these values. Now we might need to broadcast here again, because we've got a vector, and we're trying to multiply another vector by this vector, and we know that we want to have each entry of LUV multiplied by one of these. We want the two entries in LUV each to get multiplied by these things once, so that we end up with a whole bunch of things that are moving in the direction of the unit vector, but just scaled by all these values. But because we're trying to multiply a length 2 vector by a length 77 vector, it might need some help with that. So we'll go. We'll keep doing things the order we've been doing them. Times none. Okay, this really isn't D anymore. This is now the vector that is parallel to line, and we're looking for the vector that is orthogonal to the line. So we'll say para, and we'll return para. The moment of truth. Okay, so does this make sense? let's just think about it very briefly before we keep going. Let's look at line. And can we do this here? Can we return a new line character as part of a function? Apparently so. Well, kind of. It's a funny looking new line character. In terms of you can see it. All right, so just looking at these values, these are all negative, which they should be, and they are all about a third of these values over here. So I would be inclined to say these are right. Well, they are awfully large. Something's a little funky here. Why are they so large? Does it matter? Will the point that's furthest away still be furthest away? Pardon my, forgetting my basic vector math. Dot product, and projection. You have to divide by something. The dot product. I need to divide by the norm, I think. Yep. I need to divide by the norm. B onto A. So I need to divide by the norm of the projection. I'm projecting. I'm projecting onto the projection of B onto. This is the thing that I'm projecting onto. So according to, boy, you forget a little bit sometimes. It's been a minute. Yeah. So I need to divide by the. Is this right? Sure it is. Dot products and projections. Yeah. Beyond A. So I need to divide by the norm of line. That's what's missing. Divided by NP Linaug norm line. That should give us something that's more reasonable. Shouldn't be in the thousands. There we go. That's better. That's the scale of number I was expecting, not stuff in the thousands. It did make sense for the dot product, just not for the projection. So, let's see. Boy, that just totally left my head. Oh well. So, we've now got all these values that are the projection vectors onto here. So we just need to subtract all these values from all of these values. So we'll call it ortho. Hey, ortho and para. Ortho will be hype minus para for parallel. And then we want to, here we'll use D for distance. Yeah, sure, why not? And so D will just be NP let's do this the old-fashioned way, because we don't want it to think that we've got some, huge higher dimensional space. We will just, let's that should give us, okay. So we'll take ortho, and we will square the individual values, and then we will sum them. Ortho squared, and we'll sum them along the horizontal axis. Axis is equal to 1. And once we've done that, we'll take the square root. And I think that's it. Square, sum, square root. Yep, that's the recipe. 0.5. There's our square root, raising it to the 0.5th power. Let's return D and take a look. Okay. So does this match what we? Okay, so we've got something that's about 6 away, something that's about 12 away. Little higher, little higher, little higher. I think this is the max. So 1, 2, 3, 4, 5, 6 until the max, but this 6 will have an index of 5. Okay, so we did it. And so we'll our number of clusters. Same thing as should be the same thing as NC that we started out with at the beginning, is going to be NP argmax, the argument of the maximum, for the index of the maximum, which will be 5 for this 6th entry. NP argmax D, and then we'll return that value num clust. Quite a lot just to get one little number, but there you have it. And 5. Okay, that fits with the 5 clusters that we generated at the beginning. Okay. Wow, there we go, making progress. So now we know how many of our points are cluster centers, and we know which points are the densest points and which points are the furthest away from points of higher density. So we'll take that index that we made of all these sorted from high to low, and we'll take the first NC of them, and so we'll call that cluster center index. Let's see, CS IDX. It'll just be a little trimming off of distance index. So dist IDX, the first up to, we should set this to some value. And number of clusters, NCL. Sometimes I forget how to index. Do I need another thing in there? I want the first NCL values. We'll see if it throws a fit at me. Index. Okay, and it should be the first. It should be five numbers. Okay, there we go. So those are the. Oh, there's 24 again. Huh. I guess that was this time. There was just something. Not sure. Okay, so we've got the locations of our 5 densest, our 5 cluster centers. So now we want to start assigning these. We want to start assigning all points to these cluster centers. Okay, this next part, when I first saw it, was perhaps was the most difficult for me conceptually, because the example that I saw involved a lot of nested indices, and I saw it late at night, and as one will do sometimes late at night, you start to think, you start to make decisions that you wouldn't normally make when when you're well rested. And as I was looking at how to do this last step where you relate assignments, sort of going off of this picture. We're trying to say that since this dot belongs to this dot, ultimately this dot belongs to that dot. And I was thinking, well, each point only has a relationship. Many other points may have a relationship pointing to it, but each point only has a relationship that points to one other point. And I had an intuitive sense that this could somehow be represented with a matrix and with matrix multiplication. And after a little tooling around, I figured out a way to do it. And so this is my little development. It's nothing that would be huge for this problem. It might actually be a little bit slower, but I think I would like to share this now. There are, I think, some problems where it would be it's faster under very specific conditions. Okay, but before we get to that, we need to do a couple things. So just to refresh, our nearest IDX is our array of indices of points which are nearest, that are denser, and we just finished. We just calculated the number of clusters that we have, and now at this last stage we've got the indices of our cluster centers. That's what this should be, right? Dist IDX arc sort. That should be the same thing. So if we look at dist IDX, yeah, there's 24, there's 74. Okay. All right. So the first thing we're going to do is we are going to say that these points belong to themselves. Not all points, but the cluster centers. We're going to assign them to themselves. And the way that we're going to do that is we're going to make a copy of the nearest IDX. We'll say well, we'll just call it nearest copy. Nearest copy, which we'll set equal to nearest IDX, and then we will change some values in nearest copy. Nearest copy. No, so we want to set the values at the indices of the cluster centers to be themselves. So we want to say that the point that they're nearest to that is denser than them is them, which is not true, but that helps. That means that they will be sort of be pointing at themselves rather than pointing at some other point, even if they really do point at another cluster center. So nearest copy CS IDX should now equal CS IDX. All right, and let's run that, and let's take a look at nearest copy. Okay, so this is not the way to, let's go np c column stack, and let's get, oh, made a text box by mistake. npc np.arrange arrange n. Okay. Copy. There we go. Okay. So in our copy now, a few of these should be the same, and all the other ones should be different. 24 and 24, 74 and 74. Good. All right. Now we're well on our way. We're going to make a matrix of zeros that is n by n. A is equal to np dot zeros, and we have it be n by n. We could have these zeros like we have matrices that are this size, but zeros. Oh. Zeros. Got my syntax wrong. NP zeros. Okay. N. Okay, zeros, and then we'll make them ints for reasons that will become apparent. So, okay, cool. And now we're going to set the values in A where the row is going to correspond to the identity of the particle, and the column is going to correspond to the nearest particle with higher density, and with the exception of cluster centers. And we're going to set all those values equal to 1. Now this matrix has a really interesting property. This matrix has the property that when you multiply it by itself, it updates the positions of points by one. It moves them one point in the chain. So it's going to move. If this is 1, 2, and 3. Point 1, point 2, point 3. At the start, point 1 will be in the first row in the second column, and after one matrix multiplication, that entry will be zeroed out, and there will instead be a 1 in the first row, but in the third column, showing that particle 1 has gone from being assigned to particle 2 to being assigned to particle 3. That is the property that this matrix has, which I think is really cool. It's something I came across. All right, when I was playing around with this problem. Okay, so now all we need to do is multiply this matrix by itself a bunch of times, there we could go into so let's do that for I in range. And the most we would possibly need to do this would be, as many one less than the number of particles that we have in the system, because that's how many connections there are. Well, actually, it'd be two less. But in fact, there's something really cool we can do, because when we multiply. This matrix both represents the action of updating itself and its own position. So if we multiply this matrix by itself, we get some new matrix, and that matrix, if we were to multiply our old matrix by the new matrix, that new matrix is equivalent to 2 updates, because it's just the product of two of this update / position matrix. And so what we can actually do is we can repeatedly take the product of the matrix with itself, and then take the product of the product with itself. and what you get is exponentially increasing layers of assignment happening with every additional matrix update, which I just thought was fascinating when I ran across this. And in fact, the nth iteration of this is equivalent to 2 to the n minus 1 updates. So we could be really precise and try and find that specific number, but I'm just going to say, for 10, because you can't overshoot doing this. So we'll just say A is equal to A times A is equal to A matrix multiplied with A, and let's let her rip. We'll see if I made any mistakes. Okay, and then let's take a look at A. Okay, and let's sum A along the rows, so we can see which rows have values in them. So we'll sum A, and we'll go NP sum A, NP sum A axis is equal to 0, and then we will okay, so we've got 5 places by multiplying this matrix with itself. We've got 5 places that all these matrices, all these points got assigned to. So let's see. Now in the full matrix A, so this was just a quick check to make sure that everything worked out right. In the full matrix A, yes, I'm not a robot. In the full matrix A, the column that something corresponds to, the column that one entry is in is the, that's the column that it ultimately is assigned to. So let's see. It's convenient to have let's see how best to do this. What we can do, 0, 1, 2, 3, 4, 5, 6, 7. What we can do is we can find the indices. No, we've already got the indices. We don't need to find the indices. No, we do need to get the new indices. So let's do NP non-zero, I guess. So we'll say row. We'll say particle index and cluster index. Do I already use the term cluster index? I use things that are similar to it, but I don't think I do use cluster index. Okay, so particle index and cluster index are equal to NP non-zero of A. Let's see, and are there any other arguments? No. It'd help if I spelled it right. Can't spell non-zero with 0. No, that's it. And then we'll take a look at them after. NPC. I don't know if you can hear the music coming from the other room. All right, so let's do that, and then let's do this. All right, So great. 24, 31, 58, 74. And I never mixed them up, which is why they're all contiguous. That would have been maybe a little bit would have been better practice. So let's see. Now it's just a matter of graphing. We're done. I guess it might be more convenient for the graphing if I were to give these clusters numbers that started with 0, because that'll make like cycling through different colors easier. But we can see at this point the algorithm has worked. The sorting is accomplished, and so the rest is gravy. Let's what we can do. Let's open and get some more code. We could be real crummy and just hard code this thing. For I in range, let's see, what did I call it? For I in range, number of clusters. For I in range, number of clusters. And then for j in cluster index. Cluster index. If j is equal to, let's see, if j, what did I, CSIDX. If j is equal to CSIDX, if j is equal to CSIDX, I j, let's see, let me just say j is equal to I. Would that work? So let's do that, and then we'll take a let's just try it, what the heck, and then let's take another look at this. Didn't do a gosh darn thing. Shame. Okay, let's just run a couple of these things again. It's always these little things near the end. Okay. So there's our assignment. 1 through 12 assigned to particle 7. So basically, I just want to turn all these 7s into 0s. I want to turn all these 24s into 1s, and so forth. I'm sure there's a super quick, mundane way to do this. I'm just blanking right now. Brain blank. All right. So I got all excited about this other stuff. Let's see. yeah, we straight up just need a vector that goes 0, 0, 0, etc., 1, etc., 2, etc., on to 5 for I in is my loop wrong? For I in range and NCL, which is a number of cluster centers. So we start with 0 for J in the cluster index. So for each element in the cluster index, if J is equal to CSIDX I, let me just make sure that I'm doing this right. CSIDX I. Oh, CSIDX, let's go 0. Should be set. Okay, just not the order it came out, of course. It's going to be sorted here and it won't be sorted there. So, but anyway, so if J in the cluster index, let's get it to register some other condition. Print J. Let's try that. Okay, so it does register when that happens. Which 24 is 50. Okay, so it's just our condition was somehow it didn't want to do it. Well, when all else fails, store it in a dictionary, or not in a dictionary, in a list. So, what do we want to call it? Boy, I've got more things that are some kind of cluster. Let's clust.append I. Well, let's also print I just to make sure that it's interacting with I right. I don't know why it didn't work the first time. Okay, so we got some zeros, we got some ones, we got some twos, we got 3. Yeah, cool. Let's take a look at clust. Clust should be the same. Great. Oh, right. So this first is the output. All right. So now we just gotta graph this sucker. All these are gonna do is tell us the color. So let's suppress clust. But we're there. And yeah, we can get rid of that. Okay, so yeah, let's do some graphing. No. Fig 3 is equal to make subplots. Fig 3 is equal to make fig 3, and then fig 3 dot add scatter 3D, and we can just use the same points we used before because what we're going to change is the colors. So I guess it'd be right here. Same exact points because they are the same exact points and we haven't changed their indices or anything. We're just going to color them now. Doop. Let's have our mode be text because that looks fancy. Looks like you know what you're doing. And let's have our text be equal to np.arange n. And let's have let's make a vector of colors. Colors red. So this is the one part that's not flexible because I'm just setting it up for 5. But I'm sure there are ways. Red, white. Be like the Mexican flag. Green to automate this or to use a color scale. Red, white, green, blue, and red, white, green, blue. How about orange? Orange. All right. So text, and then let's see. Mode is equal to text. Text is equal to nana. Sorry, someone's calling from the other room. All right, we're back. So text is equal to np.arange. Text font colors is equal to colors, this vector of colors, indexed by clust that we made. Maybe we might need to turn clust into an array. I don't know. Yeah, is there anything missing? Well, we'll find out. Orange. I used something that's not a term. Invalid property specified. Okay. That dog keeps opening the door. Text font colors. Invalid property. So what we're trying to plug into text font colors is not, they don't like it. Let's make sure that clust even works in colors. We'll go colors. Clust. Okay, so that does work, and it's just like you would expect. So why is it suddenly not working in here? Fig 3. See, mode is equal to text. Text is equal to np image. Text font colors is equal to colors. Clust. Do I have the name of the thing right? Plotly text font color. Oh, should be color? Text font. Should be text font color? That's it. Okay. An errant S. Almost made things more difficult. Oh no. Gosh. It's all mixed up. Did it not sort properly? Oh, that would be terrible if it were the case. I think I'm using different indices. I think that's what's going on. It's applying the wrong one, which is why one is all the way red. And yeah, okay, it's applying the wrong color to the wrong cluster, and because the clusters are different sizes, that's why it is the way that it is. Oh gosh. All right, so troubleshooting. Okay. So let's print these together and see, are the changes off or what's going on? Cluster. NPC cluster IDX, and the colors clust. Do they match up? That's That's the first question. Sure looks like they do. No, they don't. Okay, well, so that's the issue. That's the issue. I need to swap these around. So I need to re-index something somewhere. You know, clust IDX, clust CS IDX is dist IDX. What if instead we took, what if we took the beginning of nearest IDX? No, that's not right. How do these get all mixed up? Let's just compare these two. They must not match. Yeah, they don't. Are they backwards? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm very tempted to throw in the towel, but this is just maddening. It's not random. They're overlapping wrong. Okay. Not the big finish I was hoping for. So, what to do? Okay. So, does cluster IDX line up with let's just go back a little bit. So NCO nearest copy, nearest IDX, nearest copy. Let's take another look at the components of A. NP C part IDX and cluster IDX. Okay. Let's did things get changed around from the original? generated what was PPC originally? Let's take a look at PPC, points per cluster. So 13, 18, 13, 15, 18. Let's see. So let's see if the order's the same one. So, yeah, 13. Okay. So 13 plus 18 is 31. So it should go to 30. Okay, cool. So the order has not changed. So how is... So it must be somewhere in this for loop that I was feeling so pleased with that things get off track. Something about my for loop logic is for the birds. So every place where for I, so for each let's sort this. Let's sort this. No, that's already sorted. Okay. For I in we do it this way? We do it directly? CS IDX for J in cluster. Could be a real let's make a counter. Counter is equal to 0. And each time we finish an iteration, we'll update. So each time, so for counter plus equal 1. Right? This should get us something that will line up. Hopefully. Okay. So these didn't line up before, do they? Do they now? No, they don't. Okay. Oh my gosh. I'm editing this out. Maybe. Or you know what? There are time codes in the bottom. You can skip my aimless troubleshooting. For I and CS. Let's take another look at CS IDX. Okay, yeah, so it's these. So it starts with 24. And then let's also look at cluster index. So many indices. Okay. So cluster index is sorted by size. The problem is that CS IDX is not. So let's sort CSIDX by size. Sorted CSIDX is equal to NP. Is there an NP sort? Sure there is. Of course there is. CSIDX. Is there anything else to know? There's only the one axis. And we want it to be sorted from, well, we want it to be sorted small to large. So let's see if it did it. It did. Okay, so let's try this again now. Oh my gosh, why is this not working? Oh. No. Seven, 8, 9, 10, 11, 12, 13. Okay. 1824s and some over 31s and oh my gosh. Why is this going wrong? Why won't this work? I get stuck right here. Not the first time. They're just plain out of order. Thirteen, 18, 13, 15, 18. That is the order that they were in. And that's, so that's it. We do have 13. Do have 13 of these to start out. So that index, cluster index, should be accurate. It's just not working up here. Okay, sorted CSIDX. So for I and CSIDX, for J and cluster, so starting with 24. Oh well. Let's look at sorted CSIDX. So starting with 7. And this 7 and this J is equal to 7, then they should append to 0, and then it should move on to this 7 And if j is equal to 1, they should append to 0 again, and again, and again, and again. Instead, so what's happening instead? Instead, when it switches to 24, it's hanging on. It's not, is it not incrementing? Print change. I mean, obviously it's going to be changing late, but so I don't actually know what that'll do for me. Print counter. Hmm. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it's starting with the second one. Somehow it thinks, does it not do them in order? Okay. Does it do them in whatever order it wants? I in CS IDX. I in range CS IDX. Range length CS IDX. Pop up. I in range length cluster center. If cluster oh wait, I never used my sorted okay, I never actually used my sorted CSIDX. Sorted CSIDX. Let's try this now. That looks more like 13, doesn't it? Oh gosh. Okay. Wow. Well, there we go, folks. That's it. That is our these are our sorted clusters. I could go a little further and call out the center, but I think that's good. I've taken up enough of your time if you've chosen to spend it watching this. So that's how you do the fast density search and find, fast search and find of density peaks. That's, I mean, ideally a little bit more smoothly than that. That's how you do it. And also with my little variation for doing a quick, simple, and exponentially increasing in speed assignment to clusters. Thanks very much, and have a wonderful, wonderful day.